So we will start last one formal session, which will be introduction to graph data. Still not any graph neural network for the day. That's for tomorrow. But since we had all the day for these sessions, I thought the last session should be an introduction to how to handle graph data. Okay, in the morning lecture, you heard about theoretically what graph is, how it looks like, age, node, blah, blah, blah. But now, since we want to learn how to code on graphs, we have to familiarize ourselves with some packages which deal with the graph data structure. And for that, we will do some PyTorch geometric stuff. So we need to learn how to represent a graph, etc. Okay. Right. So this will be using the script called introduction to graph data.ipynb, which is also there in the GitHub. And if every installation went on smooth with you, which is not the case for some of you, unfortunately, your code should print a PyTorch version and a PyTorch geometric version. And these are the latest versions. Okay. And also you should have the network X, which is required, not for the neural network, but for some plotting of the graph. And in general, network X is a very efficient graph handling library. No, it's a plotting software, but if you don't have it, you can just delete it. I mean, but you're using in this particular. No, I'm not using. I copy pasted it from my old code, so it's there. But it's on top of Matplotlib, a nice plotting software. But if you don't have it, you don't have it. Don't care. Okay. So let's see. There is. I have put some pieces of functions to visualize graph, etc. And the whole thing is that this function will take a PyTorch geometric object called graph, convert it to a network X object. So you can see g.toNetworkX, and it will plot it alongside with the adjacency matrix. So this piece of snippet of code is just for plotting a graph, and we will see how it goes. Okay, it's by the way, many times you people want to reproduce your neural network training results. One of the safest way is to set a seed for all the random engines. And you have a random engine for NumPy, a PyTorch, if you set different seeds for that, and use the graph processing using NumPy, but the training using PyTorch Geo, things won't be easily reproducible. So you can just use this code snippet to set the seed of all the random number generators all at once, and that will fix the issues of reproducibility of a training and things like that. Fine, I have put some like text and codes in the thing, but these are the concepts you already heard in the morning lecture. So what is a graph, you know? It's a set with an adjacency matrix, and the data can be put on node on the edges, as well as there will be a global data. So this is something you're aware of. Now let's do this. What's the syntax? It's important to remember. How do you define the adjacency? So first you create something called edge index. The first set is the label of nodes from which an edge starts. And the second set is the label of the nodes on which an edge ends. So what this should mean? It should mean there is, first of all, if this is the syntax, a graph should have 4 edges. The first edge should start from node 0, end at node 1. The second edge should start at 1, end on 0. And then 1, 2, 2, 3. And the whole thing is that you can define uh, a node data, something like X, a torch tensor, and wrap it with the class data. So this will create a graph in the PyTorch geometric language, and X will be dealt as a node data, and edge index will define the adjacency. Okay, so if we do this, let's try to visualize the graph. So if we try to visualize the graph, this is how it goes. What does this mean? In the standard graph sense, uh, you see the adjacency matrix, the way we defined, it was like from 0 to 1, 1 to 0, but from 1, there is an edge to 2 and 2 to 3. So this is what we call a directed graph. If all the arrows were double-headed, that should be undirected graph or bidirected graph. But here, for example, in the context of information sharing through the edges, if we consider node 1, and if there were information sitting on node 1, it can send information both to node 0 and to node 2. However, if information was sitting on node 2, it can only send information to node 3, not to 1, because there is a direction in the edge. Also, the adjacency matrix, this matrix you can visualize like the white patches are 1 and the dark patches are 0. That's what it means. So it's just visualizing the graph in the natural sense and plotting the adjacency matrix. There are inbuilt functions that whether a graph has self loops or not. So you should play with this kind of functions, go through the PyTorch geometric structure, and it returns you false, which tells that there are no self loops. What is a self loop? Where an edge starts from a node and ends up on the same node. That's called a self loop. Clearly, visually, the graph doesn't have any self loop, so it returns false. Okay. Now, fine, it doesn't have a self loop. Why don't we add few and see what comes out? So we again had an edge index, etc. And then we started visualizing the graph. So here you see there is an edge index which starts at 0, ends at 0. And there is another one which starts at 3, ends at 3. So if we plot the same thing, here you can see the self loops. And once it has self loops, in the adjacency matrix, there are entry in the diagonal element in the corresponding node index. Okay, so now you understand what is a self loop. And there is another inbuilt function. There are many functions, but which are more intuitive, I'm telling you those. Remove self loops. So it takes a graph inside. It's the adjacency matrix. And then it just removes the self loops and return you a graph without self loops. So this kind of things are there. And you can play with this. Right. And there are some interesting functions called indegrees and things like that, which act, yeah. What is going via another node?
That's not self-loop. That's a path.
Loop means the starting point and the ending point will be the same node, and it won't cross any other node in between. Okay, so because that should be one edge, and an edge can only can have one starting node and one ending node, and those two if coincide, then you call it a self loop. It will be like when there will be node upgrade by collecting information from the neighbors, it will also use the information sitting on top of itself. Right? Okay. Now, given these notations of directed graphs and self loops, there is a notation called in degree, which actually counts that how many number of edges which are converging on a particular node. So if you see that graph which was presented, the node with 1, there from 0 there were 1 edge converting there, and from 2 there was 1 edge converting on that node. So the number of in degrees are how many edges have the endpoint on that particular node. Okay, these are kind of important numbers to keep in mind because they play a role in the message passing operation. Right, now one of the most important concept of mini batching on graphs. In the morning session, we talked about forming mini batches of point clouds. And there we saw the trick that you have a variable length set, and when you merge them to form a few sets of different cardinality to form one mini batch, first what you did, you zero padded the sets which have smaller number of elements, and by that zero padding you made all the sets of equal cardinality, right? That made all the sets have same number of elements, few elements have value zeros. That's the zero padding we did. And then you could merge all of them consistently. What does it mean to batch graphs? Because graphs is some data X and an adjacency matrix. Batching means the following. You will stack the node vectors, node features, and you will make direct sum of the adjacency matrix. Keep this in mind, it's a direct sum. So if this graph has n1 nodes, the adjacency matrix was n1 cross n1. If this graph has n2 nodes, the adjacency matrix was n2 cross n2. The batched graph has an adjacency matrix of n1 plus n2 cross n1 plus n2 with the off-diagonal blocks all having 0. That's what it means to have the direct sum and the stacked over. Another thing to keep in mind that when you do information exchange among the nodes of a given graph, then you only look for which edges are connected. Now think of a batch graph. Given this is the structure of the adjacency matrix, no nodes of the second graph are connected by any edge to any node of the first graph. Is this statement clear? That's what it means to have off-diagonal elements as 0. That means within a batched graph, if you have information exchange, the information exchange will only happen within the subgraphs. Graph 2 can never send any information to any nodes on graph 1. Of information in the elements of a large batch graph. And this is what it means to batch a graph. Keep this in mind. Right. So for demonstration, you see I have picked up two graphs, like cyclic graph with 3 nodes and 4 nodes. Like one is cycle graph, one is wheel graph. Just remember, these were called data 1 and data 2. This will be 2 graphs. We will visualize these 2 graphs. So first is data 1, which is a graph with 3 nodes. And second is the data 2 with 4 nodes. So the first one is a cycle graph. Second one is a wheel graph. And you can see what the adjacency matrices are. Remember, in this visualization, the white boxes have elements 1 and the dark patches have all elements 0. Someone fainted? No. No? Okay. Now we will batch these two. Okay, let's follow the syntax of batching. How do we batch it? There is, in the PyTorch geometric data, there is an inbuilt class called batch, and it takes individual graphs as in the list. So here we formed a list of graph data 1 and data 2 and use this function from data list within the batch class, and this gives you a batch graph. Okay, so this is what we call graph B. So let's try to visualize graph B. This is what the batch graph look like. We have this set of nodes. So the total graph have this many nodes. You can clearly visualize there is no connection among the nodes coming from two different subgraphs. And that's apparent from the adjacency matrix. So here there are elements of ones. Here there are elements of ones. In the off-diagonal blocks, it's all zero. That's the concept what we just talked about. Right? So pretty simple, but just to put things in one format. So I hope later when we will do training and form mini batches of graphs, as we have to make mini batches of any data structure, it's pretty obvious what we are doing. We are stacking the graphs following the rule where the adjacency matrices from each graph will come as blocks, and all the off-diagonal blocks will be zero, direct sum of each of the adjacency matrices. Right. Again, we try to use some example. Instead of a graph, this is a structure which is called tree. But for this example, like for this discussion, there is no necessary to distinguish the core differences between a graph and a tree. But this is just called a tree, where you see, keep the structure in mind that, oops, what happened? Oh, scrolled. Oh, I can scroll it from here. I didn't know. Fantastic. Right, let's look into the tree. So this is node 0, 1 and 2. Then 1 splits into 3, 4, 2 splits into 5, 6. And then you go back to 3, it splits into 7, 8, etc. So it's just branches of a tree. Okay, now this has an adjacency matrix like this. Now, what we want to do is not core concept of message passing, although mathematically we saw what it is, but we just want to demonstrate that what message passing does visually. Now, tomorrow we will discuss in much more details that what a message passing layer is. For the time being, be satisfied that if there are node data, if you pass it through a message passing layer, it will distribute the data to adjacent nodes which are connected through edges. Okay, conceptually that's what it's doing, and I want to show you that's happening in reality. So a message passing layer, so what we are trying to do here is the following, that there were data sitting on the nodes, and for simplicity we have put the, sorry, why it's, in the whole graph the data was put only on node 0, and all the other nodes have 0 value. So that's why the color of the node is red. You can go through the code what it's doing to plot this graph, but visually what it means, that given a graph like this, initially the configuration is there was some data sitting on node 0, and all the other nodes have a data of 0 value, and hence when you draw it there is a different color. Now we have done a message passing operation where the aggregated message will be like the full part of its own. Here, remember the syntax. I means the target node which will be updated, and J means some neighboring node. And we collect the data half from the neighboring node. So if there was a target node here, and there was a neighboring node here by the green. So we use the data here and collect half of the data coming from the neighboring node. That's it. But we will go into details how this works. Now it's not something to understand, but just visually build an intuition what it's doing, that it's collecting information from the neighboring nodes and updating the node data. Okay, so initially this was what we assigned as node data. Now let's go through why it's jumping that much. No. It's okay. I know why it's jumping that much. Sorry. So initially the node data was this, and now when we pass it through several message passing layers, you see what happens. Keep a note on the colors. On the second iteration, iteration 1, these two nodes have received some data. Initially, those two nodes didn't have any data. One layer of message passing has introduced some data on these two nodes. But remember, the other nodes still haven't received the data. So what this visually tells you, that one iteration of message passing can only propagate information to nearest one hop neighbors. What is this jargon, one hop neighbors? 1 and 2 were the nodes which can be reached from 0 by passing an edge once. If you want to go to say 3 from 0, you have to cross 2 edges. So those were called 2 hop neighbors. But one instance of message passing will propagate information to nearest 1 hop neighbors, right? So here, after first iteration of message passing, only data from 0 has passed through 1 and 2, and no other nodes have received any information, right? Let's see what happens next. In iteration 2, again, all the information sitting on 0, 1, and 2 have changed. If you print the data the way I have printed, you will see. But in this case, if you print, you will see information has started propagating here and there. And finally, after a few layers of message passing, information will spread across all the nodes. Okay, so this is similar to the picture we had in morning. We drew a picture we put a picture like this, and same color code I tried to follow, that given a target node where there is some data sitting, each layer of message passing, each operation of message passing propagates data to one hop neighborhood, and it spreads and it spreads. So after few iterations of message passing, whatever information was sitting here will spread to nodes which are lying far ahead. So even if you don't build a fully connected network, just like DNN, using a message passing network, which is fundamentally different, you can still make it talk this node with this node after few iterations of message passing, and both of them will know what data was sitting there. So this is the essence of message passing neural network, from an intuitive way, that when you make that neuron diagram that all the elements are talking to each other. You don't need this. Instead, you create few stacks of message passing layer, and with much lesser number of parameters, trainable parameters, but with few iterations of message passing layer, they will start knowing each other. And that's what I wanted to demonstrate with that toy piece of code, that you have a toy layer, no weights, nothing, just repeat it. And you will see information propagating from one node to another, right? Now, while this is pretty efficient, there are inefficiencies as well. Why? If you build a graph network by making a very deep layer where there are many message passing nodes, eventually all the nodes will keep exchanging information with each other, and eventually all the nodes will start looking similar. And then the neural network will lose the expressibility it had. It wants to differentiate from data sitting on each other. Okay, so this is an effect called over-smoothing effect on graph networks. So just from this visual demonstration, remember that message passing network, what it does is exchanges information sitting on each nodes. Probably you should use few message passing layers. But if you imagine that given a graph of say order of 30 nodes and 100 edges, you will have 1000 message passing layers. That's a very inefficient construction because that network will suffer from this over smoothing problem. So this kind of things we will see, but just through this picture and the piece of code demonstration, I wanted to show you what happens, right? And finally, this is something we already discussed in morning, that right now, without using any neural network, we just shared information. Grab half of the pie from your friend and eat up, something like that. But later we will see how to process this grab data through a trainable weight parameter and update the node information sitting. So that's something we will do tomorrow. But for today, I want you to just run the code once right now of your own if you have installed PyTorch Geometric, and see how that message passing is flowing. That should work out of the box.
PyTorch geometric run without GPU?
Yes. Nothing, I mean, nothing requires GPU. No software can demand you to install GPU. On any hardware architecture, it should run. Okay, so now we are not doing any neural network training. We didn't introduce any graph neural network, but I just wanted to give you a visual intuition building of what message passing does. So if you have questions regarding this, about construction of a graph using PyTorch geometric, mini batching of graphs, and what message passing is conceptually doing. Try the notebook out and ask questions. I don't have anything more to discuss for the today because the next lecture will be just building a graph neural network, and that will require some coding, etc. I don't want to dump you with that today. That's for tomorrow.
The number of message passing layers or the epochs?
Sorry?
So
No.
by the iteration, like you.
Oh, those were number of message passing layer. Here we didn't do any training, so number of epochs doesn't arise.
So each message passing layer can only hop once.
Right. Okay. Information exchange can only happen within one hop neighbors. It's not a question of can, it will. Yeah. Okay. And then Let's see. Should I do message? No, no. This will be heavy on you. I will do this tomorrow. Right. So if you guys can run the, first of all, can you download the notebook and run yourself? Right? Can you guys try something like a cyclic graph with 5 nodes and then introduce some edge data on this following the syntaxes which we have introduced? Right now we just put node data on the graph, no edge data. Can you figure out how to introduce edge data and what will be the shape of the edge data? Try that out, because remember we had node data, we had edge data, and we have global data. So when we start doing neural networks with these data structures, you need to have a very good grip on what are the shapes of these data structures and how these shapes are changing with each layer of message passing network. So in the example notebook, I haven't introduced any edge data. Try it. Yeah, but it shows you there exists an edge, but there I didn't put any data on the edge. Okay, so now I want you to figure out how to put data on the edge, and given some graph with say 5 nodes and 10 edges, what will be the shape of the data of node data versus edge data? Something like that. Because from my side, I don't want to introduce anything more today. I want you to play with this basic definition of graph using PyTorch geometric dataset structure. And once you have done that, I will finish it, and probably Ilham will discuss something else, right, Ilham? Yeah. So let's try this for the next 10 minutes, and then I will stop for the day. But the core questions from this 40-45 minutes, that how to define a graph, how to make mini batches, and what's happening intuitively by message passing, this should be absolutely clear. Also, remember that when we will talk about neural networks on graph, there will be things like a function which takes input a graph and gives output either a graph or some tensor or anything else. So from tomorrow, we will see how to write functions on graph. So today, make sure it's completely clear what the graph structure is and how to associate data on the graph. Unless that's clear, we can't write functions on graph. Another small task I want to give you. In the morning, we talked about permutation of the graph, right? So given now you know how to permute a graph from the slides. So can you try permuting a graph of your own? I haven't included that inside the notebook, but remember the graph was defined by X and A. And you can try to, let's say a graph has 4 nodes, define your own favorite adjacency matrix on that, and permute the nodes as well as the edges and plot the graph like the original graph and permuted graph to see what has changed. Because you should have a visual intuition of these are just equations. But now that in the notebook I have shown you how to plot a graph and its adjacency matrix, you should be able to visualize of your own before and after the permutation has been applied, how a graph changes.
And it says layer. It can't figure out. Name layer is not in this draw graph color. Then you say article color.
No, but there was a place where the message passing layer was defined. So you just write layer equal to my MP layer. I think the cell was there. I accidentally deleted and so you just write layer equal to my MP layer, and that's it.
Open close bracket, nothing else.
Can you show me?
This
Yeah, exactly.
This one. This one.
No, did you run it again?
Yeah, I ran. This one I ran it here.
Run it once.
So you have to redefine the function.
Yeah. Because if you just define but don't execute the cell. Do you think something else should be defined just as 0th introduction?
No, actually, layer equal to my layer was defined afterwards.
Oh, okay.
Yeah, it's there.
Yeah.
Again, something is, I think SRC is again missing. Source, so torch index, source, 0 source index. So source index, so what is source? Is that layer?
No, so gr.age index. So you remember age index was 2 pieces of data. One was the labels of the originating nodes, and one was the target nodes. The source 0 will like gr index 0 will give you the source labels.
So I simply say gr.x.
Not x, index. X will be the data on the nodes.
Okay. So okay, that is a source index. That is a source index. But what is source? So source without this 0, right? Problem is the variables source is not defined. It says.
The source should be x on gr index 0. Could you define any permutation on the graphs? Can anyone show me? Want to try?
So for this running, post myself. So post myself. The device is equal to CPU. Reason is because this guy is occupying the GPU.
Okay, I see.
Just close this and
Restart. Okay, during the evening time, please try to give this permutation a try. Okay, I would love to see you guys coding. So today I don't have anything more. If you have any questions on how to define a graph, mini batch, all this stuff, what is with loops, without loops, etc., etc. Otherwise, I will stop for the day and maybe Elam will take over. Okay, so give it a try, this permutation and etc. And then Elam will start at 5.